Hello everyone, welcome to the first video in the Introduction to Astrophotography Series. In this series we will be delving into many differing facets of the field of astrophotography, such as exposure and field of view calculations, equipment recommendations, photographic techniques for capturing meteor showers and satellites, and much more. Here is a list of topics covered in the video, so if you are interested in a specific topic you can skip to the related section. This particular video will focus on a comprehensive coverage of the most commonly employed celestial coordinate systems, which are used to locate and track celestial objects such as stars, planets, and deep sky objects. In addition to explaining the function and use of celestial coordinate systems, we will also cover related topics, such as sidereal time, the Julian Day System, and the effects of axial precession and nutation. The two celestial coordinate systems we are going to be focusing on today are the horizontal system and the equatorial system. Celestial coordinate systems are based upon spherical coordinates, where the separation of points on a three-dimensional sphere are measured via vertical and horizontal angular projections from an origin point. The most commonly known spherical system is the geographic coordinate system of latitude and longitude, which serve as the vertical and horizontal angles respectively. The great circle is the origin plane of the spherical system, bisecting the sphere into two separate hemispheres and serving as the equatorial region of the sphere, just like the equator serves as a division between the northern and southern hemispheres. Any other parallel planar projections above or below this great circle create circles which have a radius less than that of the great circle, and as such are referred to as minor or lesser circles. Examples of minor circles in the geographic coordinate system would be the Arctic or Antarctic circles or the tropics of Cancer or Capricorn. Both of the celestial systems we will be examining have names derived from their origin points, which define the great circle used for measuring the angles in each system. The horizontal system is based on the observer's local horizon, meaning that the projection of the system is constant for any location on Earth. The equatorial system is measured relative to the projection of the celestial equator, which changes based on the observer's latitude. Since the projection of the horizontal system is constant, the coordinates of any given object will differ for different locations, whereas the equatorial coordinates, barring local hour angle and the effects of precession, for an object will remain constant for all locations. The two coordinates in each system are similar in their function as they measure the vertical and horizontal angles of an object based on the origin point or great circle of each system. The embodiment of the vertical angle in the horizontal system is altitude, which is used to measure the vertical angular offset relative to the horizon, which represents an altitude of 0. Positive altitude represents angles above the horizon with a maximum of 90 degrees, while negative altitude represents angles below the horizon with a minimum value of negative 90 degrees. Azimuth is the second coordinate in the horizontal system and is used to measure the horizontal angle relative to true north clockwise from 0 to 360 degrees, with each successive cardinal point eastwards of north representing an increase of 90 degrees from the previous, meaning that north is 0, east is 90, south is 180, and west is 270. The first coordinate in the equatorial system is declination, which is used to measure the vertical angle relative to the celestial equator, which represents a declination of 0 degrees. Declinations north and south of the celestial equator represent positive and negative angles respectively, with the maximum declination of 90 degrees representing the north celestial pole and the minimum declination of negative 90 degrees representing the south celestial pole. The horizontal angle in the equatorial system can be one of two related coordinates depending on the situation or preference. Right ascension is the coordinate which is most commonly associated with the equatorial system and is used to measure the horizontal angle eastwards along the equator relative to the vernal equinox. The alternate coordinate is referred to as local hour angle, which measures the horizontal angle westwards with the apparent motion of the sky relative to the local meridian, which is a celestial landmark running from directly north to directly south in the local sky. Both of these coordinates are interchangeably measured from 0 to 360 degrees or 0 to 24 sidereal hours. The equatorial system can be thought of as the celestial equivalent of the geographic coordinate system, as both are equator-centric systems. You can imagine overlaying the spherical projection of the sky onto the Earth, aligning the two using the equator and origin of each respective system. Now we can measure the angular position of any object in the sky relative to the equator just like we would measure the coordinates of a location on Earth, with declination serving as the equivalent of latitude and right ascension serving as longitude. This analogy is also useful for explaining the dependence of the system's projection upon the latitude of the observer. The easiest way to visualize the projection at a given location is to imagine a line spanning from the center of the Earth to the location. Then imagine rotating the Earth so that the line is vertical. This is how the system will appear at the given location, with the horizon being perpendicular to the imaginary line. For instance, if we are located along the terrestrial equator, then the celestial equator will be directly above our heads spanning east to west, with the celestial poles located directly on the horizon. If we are located at a latitude of 30 degrees north, then the celestial equator will be tilted 30 degrees to the south, with the north celestial pole having an altitude of 30 degrees and the south celestial pole having an altitude of negative 30 degrees. If we were instead located at a latitude of 30 degrees south, then the opposite rotation would occur. The equator would be tilted 30 degrees to the north, the south celestial pole would have an altitude of 30 degrees, and the north celestial pole would have an altitude of negative 30 degrees. Overall, the functionality of the two systems are similar. Basically, an equatorial mount is just a horizontal mount tilted at an angle equivalent to the complementary latitude of the observer, which is equal to 90 degrees minus the latitude. This is the concept behind a device referred to as an equatorial wedge, which is used to rig a horizontal mount into functioning like an equatorial mount by creating an angle equal to the latitude of the observer between the horizon and the mount. However, this is only practical for light loads since the gravitational force acting on the load is off-axis, which affects the precision of the motors via stress and backlash. Equatorial mounts commonly employ the use of counterweights attached along the opposite side of the axis of the load's center of mass to offset this loading factor. The horizontal system is useful for finding objects, as we intuitively use the horizon as an origin point for measuring the location of objects using up, down, left, and right as directions. However, as a consequence of the Earth's rotation, the apparent motion of celestial objects across the sky corresponds to the celestial equator, not the local horizon. This compensation for the Earth's rotation makes the equatorial system useful for tracking objects over longer periods of time, as the movement of only one axis is required to track an object as the Earth rotates, as opposed to the translation in two axes required by the horizontal system. Because of this difference, the horizontal system is primarily used for visual observation and short planetary exposures, whereas the equatorial system is used for longer deep sky exposures. It should also be noted that equatorial mounts tend to be more accurate in their alignment, as the initial alignment is usually made with the polar finder scope. The horizontal system can be used for longer exposures, but motion blurring may be present in the image as tracking requires movement in two axes. Before we dive into a detailed explanation of the systems, we need to cover some important celestial landmarks which are employed in the following sections. We will label the axes of our example sphere to assist in the visualization, with the center of the sphere serving as the origin. The axis representing north and south will be the y-axis, while the axis perpendicular to y representing east and west will be the x-axis. And the vertical axis orthogonal to the horizontal plane will be the z-axis. Next, we will bisect the sphere by creating a great circle in the horizontal plane and label it the horizon. The horizon divides the celestial sphere into two hemispheres. The upper blue hemisphere represents the visible sky, and the lower red hemisphere represents the portion of sky obscured from view. Here's a simulation of how the horizon would appear to you if you are outside at night looking at the sky. Next, we will label the highest positive point on the sphere in the z-axis as the zenith, and we will label the lowest negative point on the sphere as the nadir. The zenith represents the highest point in your local sky, while the nadir represents the lowest. The zenith is located at a 90-degree angle relative to the horizon, while the nadir is located at a negative 90-degree angle. If you imagine you are outside and looking at the sky, the zenith would be the point directly above your head, while the nadir would be the point directly below your feet. Next, we will add two great circles perpendicular to the horizon, one running from north to south intersecting the zenith and nadir, which we will label the local meridian. The other will span east to west, also intersecting the zenith and nadir, and we will label this one as the prime vertical. You can think of these two great circles as projections of the cardinal points onto the celestial sphere, effectively dividing it into four 90-degree sections. If you are outside facing north, then the meridian would be an imaginary line running from directly north in front of you to south directly behind you, intersecting the zenith above your head and the nadir below your feet. The prime vertical is similar, except it is at a 90-degree angle relative to the meridian spanning east to west. Now that we have some celestial landmarks, we can take a look at the first coordinate in the horizontal system, which is azimuth. You can think of azimuth as being similar in function to a compass, as it measures angles in the horizontal plane eastwards relative to geographic north, where the horizon intersects the meridian. Viewing the sphere from above, we will designate north as 0 degrees azimuth as it serves as the origin point of the coordinate. Each successive cardinal point eastwards or clockwise from geographic north represents an increase of 90 degrees from the previous, with each cardinal point coinciding with either the local meridian or the prime vertical. This means that east represents an azimuth angle of 90 degrees, south represents 180 degrees, and west represents 270 degrees. Next, we will divide the 4 90-degree sections into 8 smaller sections, each representing a great semicircle and 10 degrees in azimuth, starting at 0 to the north and increasing eastwards. Viewing the sphere from an axonometric perspective, we can see that the 36 great semicircles representing azimuth run from the zenith down to the nadir, bisected by the horizon. This is the azimuth coordinate. It is responsible for measuring angles on the horizontal plane along the horizon. The next coordinate in the horizontal system is altitude. If azimuth determines the angular position of an object in the horizontal plane relative to north, then altitude is responsible for determining the angular offset from the horizon in the vertical dimension. Since the horizon serves as the origin plane for altitude, we will label it as 0 degrees altitude. The blue hemisphere above the horizon represents positive altitudes as opposed to the red hemisphere below the horizon, which represents negative altitudes. The zenith, which is located 90 degrees above the horizon, represents the maximum value of altitude of 90 degrees, while the nadir represents the minimum altitude value of negative 90 degrees. Next, we will create a series of 16 cones split evenly up and down the z-axis, with the horizon serving as the plane of symmetry. Each cone will originate from the center of the sphere and have side lengths equal to the radius of the sphere. For positive altitudes, each cone above the horizon will have an increasing exterior angle based on a 10-degree increment from the previous, meaning that the angle subtended between the horizon and the edge of the first blue cone will be 10 degrees. The second blue cone will have an exterior angle of 20 degrees. The third will have 30 degrees, etc., with a maximum value of 90 degrees at the zenith. For negative altitudes, each cone below the horizon will have a decreasing exterior angle based on a 10-degree increment from the previous, meaning that the angle subtended between the horizon and the edge of the first red cone will be negative 10 degrees. The second red cone will have an exterior angle of negative 20 degrees, the third will have an angle of negative 30 degrees, etc., with a minimum value of negative 90 degrees at the nadir. The angle between the horizon and the edge of a cone is equal to a given altitude. The complementary angle to altitude is referred to as the zenith angle or the co-altitude, which is equal to 90 degrees minus the given altitude, and is represented by the interior angle of a given cone, between the edge of the cone and the z-axis. From an axonometric perspective, we can see that the outer edges of the cones create minor circles on the surface of the celestial sphere. These cones represent the altitude coordinate, with the cones above the horizon representing positive altitudes and the cones below the horizon representing negative altitudes. Now that we have covered both coordinates in the horizontal system, let's take a look at an example to see how the system is used to find celestial objects. Here we can see a stereographic view of the night sky. The green line running from north in front of us represents the local meridian, while the purple line spanning east to west represents the prime vertical. The orange horizontal arcs between the cardinal points represent the azimuth coordinate, while the vertical grid lines represent the altitude coordinate, with both in increments of 10 degrees. The point of convergence for the coordinates is the zenith, located at a 90-degree angle to the horizon and intersected by both the local meridian and the prime vertical. Here we can see the star Vega, which we will be using for our example. Using the grid of the horizontal system, we can see that Vega is currently located about 61 degrees east of north, indicating that Vega's current azimuth is about 61 degrees. Next, we will use the altitude grid to determine that Vega is currently located approximately 52 degrees above the horizon, indicating an altitude value of about 52 degrees. Next, we will take a look at Regulus, which is currently located to the west. Since azimuth is measured eastwards from north, we can subtract Regulus's westward angle from 360 to determine its current azimuth. Using the azimuth grid, we can determine that Regulus is currently located about 83 degrees west of north. After subtracting 83 from 360, we arrive at an azimuth coordinate of 277. Next, we will use the altitude grid like we did before to approximate Regulus's current altitude, which is about 11 degrees. The angular position of every celestial object in the sky can be measured using the horizontal system. However, the horizontal coordinates of a given object are constantly changing in two axes due to the Earth's rotation. The next coordinate system we will be examining addresses this issue, allowing for more static coordinates for any given celestial object compared to horizontal coordinates. The equatorial system is based on a projection of the geographic poles and equator onto the celestial sphere, so it can be thought of as a celestial equivalent of terrestrial latitude and longitude. The equatorial system is equator-centric, meaning its angular coordinates are measured relative to the celestial equator. Unlike the horizontal system, the projection and layout of the equatorial system in your local sky is based on your geographic location. The embodiment of the vertical angle in the equatorial system is declination, abbreviated as dec, which is comparable to geographic latitude. The horizontal angle in the equatorial system is either right ascension or local hour angle, abbreviated RA and hour angle respectively, which are similar in function to geographic longitude. I'm guessing that the majority of viewers live in the northern hemisphere, so we are going to be focusing on the system as it relates to the North Celestial Pole. To make things a little easier, I'm going to be using the abbreviations for the northern and southern celestial poles, which is NCP and SCP. You can imagine the coordinates of the equatorial and horizontal systems as being similar in function. Declination measures apparent angular offset from the equator just like altitude measures relative to the horizon, and both create minor circles on the celestial sphere, aside from their origin points, which are major circles. Azimuth and right ascension or local hour angle are also similar in that they both divide the celestial sphere into major semicircles and are measured along the plane of origin. The only difference is that right ascension or the local hour angle coordinates are perpendicular to the equator and intersect both poles, while azimuth is perpendicular to the horizon and intersects the zenith and nadir. Basically, the coordinates of both systems are identical in function, except in the equatorial system the poles function like the zenith and nadir and the equator functions as the horizon. The first and most important concepts we need to address are the celestial poles and equator. These can be imagined as projections from the Earth onto the celestial sphere. The celestial equator is a projection of the Earth's equator, creating a major circle on the celestial sphere and dividing it into two hemispheres, north and south, with the poles located at 90-degree angles relative to the equator. The celestial poles would be lines extending from 90 degrees north and south latitudes, creating points at opposite ends of the sphere. Since these celestial points are based on the Earth, they do not change very often over time. We're going to talk a little bit more about precession and epochs later on. The next step is to determine where these celestial markers would be projected in your local sky based on compensation for your terrestrial location. Let's take another look at our example sphere and suppose that we are located at a latitude of 0, which would be any position on Earth located along the equator. Since we are located on the terrestrial equator, the celestial equator will overlap the prime vertical at a 90-degree angle relative to the horizon, spanning directly east and west along the x-axis and intersecting the zenith and nadir. Since the celestial equator is a great circle, it will divide the sphere into two hemispheres. The blue hemisphere represents the north celestial hemisphere, and the red represents the south celestial hemisphere. The celestial poles are located at 90-degree angles relative to the celestial equator, which means both poles will be located on the horizon with an altitude of 0. The NCP will be located at an azimuth of 0 degrees or directly north, and the SCP will have an azimuth of 180 degrees or directly south. Note that the azimuth of the poles never changes, regardless of your location. The celestial equator will also always intersect the horizon at directly east and west, and the celestial poles will always be perpendicular to the equator regardless of your terrestrial location as well. Now, since we have a basic idea of how these projections would appear from a location of latitude 0, we can examine how they would change relative to latitudes above or below the equator. Basically, for a given latitude, the entire equatorial system rotates based on the latitude's angular separation from the terrestrial equator, meaning that the poles have an altitude either equal to or opposite of the given latitude. A northern latitude causes the apparent position of the NCP to move upwards in altitude relative to the local horizon at an angle equal to the latitude's angular separation from the equator, while the SCP moves below the horizon at an equal but opposite angle. This also means that the apparent position of the celestial equator will also tilt relative to the prime vertical at the same angular offset as the poles. The apparent rotation of the poles corresponds to the rotation of the entire coordinate system at an angle of the same magnitude and direction as the poles. A southern latitude causes the opposite effect of a northern latitude. The system rotates in the opposite direction, causing the apparent altitude of the NCP to move below the horizon while the SCP appears to increase in altitude. At a latitude of 90 degrees north, which would be the north terrestrial pole, the NCP would be located at the zenith, with the celestial equator overlapping the horizon. We will touch a little bit more on this concept in detail later on, but now we are going to look at the actual coordinates used in the equatorial system. The first coordinate in the system is called declination. As mentioned before, it's similar to altitude, but measures an object's angular offset relative to the celestial equator instead of the horizon. Declination is a relatively constant coordinate for distant stars compared to the span of a human lifetime. In the equatorial system, it defines the apparent circular path that a star moves along as the Earth rotates, with the apparent radius of that circle determined by the declination's angular distance from the equator and poles. Let's take another look at our example sphere again from the side view, with the same celestial landmarks we labeled previously, this time located back at a latitude of 0 along the equator. Since the celestial equator is considered the plane of origin of the system, we will label the equator as 0 degrees declination, with the NCP representing 90 degrees declination and the SCP representing negative 90 degrees. The blue hemisphere represents positive declination, while the red hemisphere represents negative declination. Imagine the series of cones again, but this time they are located along the y-axis instead of the z-axis. 8 cones are in the positive or north direction, and 8 are in the negative or south direction, with the celestial equator acting as the plane of symmetry. Since the celestial equator represents 0 degrees in declination and the NCP represents 90, each cone out from the equator has an exterior angle that is 10 degrees more than the previous relative to the equator. So the first will have an outer angle of 10 degrees relative to the equator, and the cone after that will be 20 degrees, etc. For negative declinations, the SCP represents negative 90 degrees declination. So each cone out from the equator will have an exterior angle that is 10 degrees less than the previous. Each cone represents 10 degrees in declination, so the largest cone closest to the equator would have a declination of 10 degrees, and the smallest cone near the NCP would have a declination of 80 degrees. Technically, the celestial poles should be represented as cones here since they are angles of declination, but since they are at a 90-degree angle relative to the celestial equator, they would be represented as infinitely thin lines. The complementary angle of declination is called the polar angle. It is represented by the interior angle of the cones and is used when converting between coordinate systems. The polar angle is measured relative to the plane of the poles to the cone's edge and is therefore equal to 90 minus the declination of any given cone. Since the celestial equator has a declination of 0, it's a great circle. Every other declination is represented by a minor circle with an apparent radius based on its angular position relative to the equators or poles. Basically, the apparent path of a star of a specific declination is determined by the angular distance of the declination from the equator. It also determines the angular radius of the circular path of the object as it completes a rotation around the axis of the poles. Here's an example of how the declination coordinate would appear to you if it were traced in the sky. The layout of the system in this example is based on my location in Florida at a latitude of about 27.3 degrees north, so we can see that the NCP is located at an altitude equal to that latitude. The declination coordinates are the circles radiating out from the NCP, just like the circles created by the cones representing declination on the example sphere. As time passes, watch how the stars stay fixed in their position relative to the circles of declination. This is why equatorial mounts are useful for long exposures. Since the declination of an object is constant, the mount only has to slew in one direction to compensate for the Earth's rotation. Here's another view from the same latitude, this time looking west. We can see the celestial equator is separated from the prime vertical at an angle equal to the latitude, which is also equal to the altitude of the NCP. The declination coordinates in this view are the lines which are parallel to the equator. From this viewpoint, you'll notice that the declinations closer to the celestial equator have apparent angular radii which are much larger compared to the ones near the NCP. This is why they appear to be arcs when in fact they are actually circles like in the example sphere we saw earlier. Watch as time passes here, and again you'll see that the star's positions stay fixed relative to the declination circles. For a given interval of time, the stars with declinations closer to the celestial equator appear to move faster than those closer to the poles. This is due to the fact that the apparent angular radius of the paths of stars closer to the equator is larger. The difference in the apparent speeds of stars due to Earth's rotation is referred to as apparent angular velocity. The apparent angular velocity of a star is dependent upon the declination of the given star, and is measured relative to the observer at the center of the sphere in terms of horizontal coordinates. Here's an example of the difference of apparent angular velocity of objects located at different latitudes of a sphere. Any given angle, labeled theta in the example, which originates at the center of the sphere, traces a minor circle on the surface of the sphere, with a circumference corresponding to the radius, labeled r theta, which is subtended by the cosine of the angle. To simplify things, the radius of the sphere in the example will be 1, meaning the great circle at the equatorial region will have a radius of 1, and any other minor circle on the sphere will have a radius equal to the cosine of the given angle. Viewing the sphere from above, we can see that an object located on the surface of the sphere at the given angle will follow a predetermined path based on the circumference of the corresponding minor circle, with the total path length of a single rotation being equal to 2 times pi times the cosine of theta. Therefore, the velocity of an object along this path is equal to the circumference of the minor circle divided by the rotational period, t. Using this equation, we can see that objects located on the great circle in the equatorial region will have the fastest velocity since the cosine of 0 is equal to 1, while the axis of rotation at the poles will have a velocity of cosine of 90, which is equal to 0. We can compare the relative speed of two objects on the sphere's surface using their angular height, labeled θ1 and θ2, by dividing the velocity of θ1 to θ2. This can be rearranged into the ratio of the velocity and radius of 1 being equal to the ratio of velocity and radius of 2. This means there is a constant relationship between all locations on the sphere. In order to conserve this constant relationship, if the velocity of a point changes, then its radius must change to be equal to the system's constant. This is a basic example relating an object's angular position to its apparent velocity. In future videos, we will take a look at deriving the speed of an object to determine its apparent angular velocity for static astrophotography exposures. The difference in speeds of these objects implies that for any location on Earth, objects located on the celestial equator will always appear to travel the fastest, and the celestial poles will always stay stationary since the poles serve as the axis of rotation. The second coordinate in the equatorial system is technically right ascension, but we will be focusing more on local hour angle since it is an important variable for converting between the various coordinate systems. To simplify things, I will refer to right ascension as RA, and local hour angle will be simplified to hour angle. If declination determines the star's apparent circular path, then the hour angle or RA determines the apparent angular separation or sidereal time offset between one position along the path to another relative to the poles and equator, or the apparent angular arc subtended by a star from one point to another as measured from the celestial poles. When measured relative to the celestial poles, all stars subtend the same apparent angle as they rotate, which is equal to about 15.041 degrees per solar hour or 15 degrees per sidereal hour, as opposed to the apparent angular velocity when measured via horizontal coordinates. Before we examine RA and hour angle, we need to cover some prerequisite topics which will assist us in the explanation of these coordinates. The sidereal hour is an essential unit of time for both RA and hour angle. A sidereal hour is equal to 59 minutes and 50.17 seconds, and is different from a standard hour as it is based upon a sidereal day, which is 23 hours, 56 minutes, and 4.1 seconds long, compared to 24 hours in a solar or standard day. The difference is due to the fact that the sidereal day is based on the angular rotation of the Earth's orbital motion around the Sun. Ignoring seasonal time fluctuations, a standard 24-hour solar day is based on the length of time the Sun takes to complete one apparent rotation across the sky from a given location on Earth, measured from its starting position on the meridian at solar noon. A sidereal day is also measured using the local meridian, but is based on the amount of time it takes for a distant star to complete one apparent rotation across the sky, which is about 3 minutes and 55.9 seconds shorter than the Sun's apparent rotation. To visualize the difference between the two, imagine you are facing north towards the local meridian, and that a star and the Sun are located at exactly the same apparent position in the sky on the meridian. Exactly one sidereal day later, the star will have completed its apparent rotation and be located back on the meridian, while the Sun will appear to be slightly to the east behind the star, with an apparent angular separation of 58 arc minutes and 58.5 arc seconds, or approximately 0.9829 degrees. 3 minutes and 55.9 seconds later, or one standard day from their starting point, the Sun would be on the meridian and the star would be slightly ahead of it at the same apparent angular separation. The difference in apparent travel time is due to the fact that the Earth is rotating around the Sun in an elliptical orbit. Although the length of the sidereal year fluctuates based on axial precession, its length is based on the time required for the Earth to complete an orbital cycle as compared to a relatively static reference frame of distant stars, with an average duration of approximately 365.256 days. So one orbital cycle of 360 degrees of rotation divided by the period of that cycle, which is 365.256 days, results in approximately 0.986 degrees per day, which can be converted to time to about 3.942 minutes. So the Earth is required to rotate 360 degrees plus the extra 0.986 degrees due to its orbital motion in order for the Sun to complete an apparent rotation across the sky to observers on Earth. This is why there is a discrepancy in time between a solar and sidereal day. The next topic we need to address is the conversion between units of angles in sidereal time. Rate ascension and hour angle are interchangeably measured in either degrees or in sidereal hours, minutes, and seconds. 1 hour represents 15 degrees of arc. 1 minute, or 1/60th of an hour, represents 15 arc minutes, or a quarter of a degree. And 1 second, or 1/3600th of an hour, represents 15 arc seconds, or 1/240th of a degree. To convert minutes and seconds into decimal hours, divide the minutes by 60 and the seconds by 3600, and add the results together, and then add the hours. This will give you the decimal version of the time. To do the reverse, subtract the integers representing hours from the decimal version of time, then multiply the result by 60 and subtract the resulting integers representing minutes so that only decimals remain. Then repeat the process by multiplying by 60 again. This final result will give you seconds. To convert the decimal versions of time to degrees, multiply by 15, and to convert degrees to time, divide by 15. The final topic we need to address is the ecliptic, which contains the origin point for RA, called the vernal equinox. If the Sun's apparent path over the course of a year was traced upon the celestial sphere, it would create a great circle which would be inclined to the celestial equator at an angle equal to the axial tilt of the Earth, which is equal to about 23.4 degrees. This apparent path is referred to as the ecliptic. Since both are great circles, there will be 2 points on the celestial sphere where the ecliptic and the celestial equator intersect. These 2 points represent the apparent position of the Sun during the vernal equinox in spring and the autumn equinox. The solstices are located at 90-degree angles relative to the equinoxes along the ecliptic, with the summer solstice located at the most northern point relative to the celestial equator, and the winter solstice located at the opposite point to the south. The etymology of the ecliptic is based on the fact that both the moon and the sun must be located on the ecliptic plane for an eclipse. Now that we've covered the prerequisites, we can move on to the actual coordinates themselves. As mentioned previously, these coordinates are similar in form to azimuth, but while the apparent position of azimuth is constant, the apparent position of a given RA coordinate is constantly changing since the reference frame for RA corresponds to the rotation of the Earth. This means that a celestial object will retain its given RA coordinate over time. In this sense, the hour angle coordinate is opposite to right ascension. It is similar to azimuth since its layout in the sky is constant based on the local meridian, but a star will have a constantly changing hour angle coordinate as it completes a rotation around the sky. For a basic overview of RA and hour angle, let's take another look at our example sphere from a latitude of 0 or along the terrestrial equator. The hour angle or RA coordinates can be thought of as 24 great semicircles, one for each sidereal hour, running from the NCP to the SCP, bisected by the equator. Each successive arc represents one sidereal hour or 15 degrees. Although their apparent form is conceptually similar, RA and local hour angle have different origin points and they are measured relative to different celestial markers. The celestial equator and vernal equinox for RA and the celestial equator and local meridian for hour angle. To understand the difference between these two coordinates, we will examine the sphere from the origin point at the center, facing north towards the local meridian. Right ascension measures angular or sidereal time offset relative to its origin at the vernal equinox, and is measured east to west along the equator. Although the apparent position of the vernal equinox in the sky changes with the local sidereal time, we will simplify things by defining its current position on the example sphere directly west on the horizon. The vernal equinox represents the origin point for RA, so we will label it as 0 degrees and 0 sidereal hours. East arc eastwards or clockwise from the vernal equinox represents 15 degrees or 1 sidereal hour of RA, from 0 to 360 degrees or 0 to 24 sidereal hours. As time passes and the Earth rotates, the RA coordinates will rotate westwards, which is counterclockwise from this point of view. So 6 sidereal hours from the starting point, the RA coordinates will have moved 90 degrees counterclockwise. 1 sidereal day from the starting position, the RA coordinates will have returned to their initial positions. The local hour angle specifically measures a given star's angular and sidereal offset from the observer's meridian, measured according to the apparent movement of the sky westwards along the equator. Unlike RA coordinates, which rotate around the sky, the position of a given hour angle coordinate is fixed relative to the local meridian, similar to how azimuth is fixed to the local meridian. Since the local meridian is the origin point for local hour angle, it will be labeled as 0 degrees and 0 sidereal hours. As the orientation of local hour angle is based on the apparent rotation of the sky, each arc westwards or counterclockwise from the meridian will increase by 15 degrees or 1 sidereal hour relative to the local meridian, from 0 to 360 degrees or 0 to 24 sidereal hours. Since the projection of the hour angle coordinates are constant relative to the local meridian, a star's hour angle coordinate changes based on its apparent angular separation from the meridian as it rotates around the poles, as opposed to its RA coordinate, which stays constant due to the fact that the RA frame of reference is rotating at the same apparent rate as the star. Looking north to the NCP, you can imagine the hour angle coordinates as being similar to a clock which is flipped horizontally, with the NCP acting as the clock's center and the celestial equator acting as the edge of the clock where the hour numbers would be located. This clock runs counterclockwise with the apparent motion of the sky and completes a cycle every 24 sidereal hours, as opposed to a regular clock which completes a rotation every 12 standard hours. Just like a normal clock is divided into 12 sections, imagine 24 lines emanating from the NCP and running to the celestial equator, cutting the sky into 24 equal segments with the same angular separation of 15 degrees. Now imagine a star which is located on the meridian, which would be the 12 o'clock position on a regular clock. The star in this example functions like the hour hand on a regular clock. As the Earth rotates, the star appears to move west along its circular path. After 1 sidereal hour, the star will have moved from the meridian to the imaginary line running from the pole to the celestial equator, representing 1 hour or 15 degrees relative to the meridian. This process will repeat until the star has arrived back at the meridian after 24 sidereal hours, at which point the entire process will repeat. There are some very important relationships between the hour angle coordinate and the horizontal coordinates of an object, which make it an essential component in the conversion between the systems. The following rules are true for any latitude on Earth. A celestial object located at its maximum altitude will be located on the meridian, and will therefore have an hour angle of both 0 and 24 hours or 0 and 360 degrees, since it is located along the meridian above the pole. An object located at an altitude equal to the latitude and at its most westerly azimuth will have an hour angle of 90 degrees or 6 hours, since it is located at a 90-degree angle relative to the meridian at an altitude equal to the plane of the poles. An object at its lowest altitude will be located along the meridian below the poles and have an hour angle of 180 degrees or 12 sidereal hours. And an object located at an altitude equal to the latitude at its most easterly azimuth will have an hour angle of 270 degrees or 18 hours. Let's take a look at an example star to see how RA and the local hour angle are measured for celestial objects. Imagine we are facing towards the NCP and the meridian. Suppose that the vernal equinox is located at an hour angle of 30 degrees or 2 sidereal hours, which implies that the RA coordinate of 2 hours is located on the meridian. There is a star with an RA of approximately 6 hours, meaning it will be separated relative to the vernal equinox by 15 times 6, which equals 90 degrees. Since the vernal equinox is currently located 30 degrees westwards of the meridian, the star will have an hour angle of 300 degrees or 20 sidereal hours. This is calculated by subtracting the hour angle of the vernal equinox, which is 30 degrees, from the longitudinal separation between the vernal equinox and the star, which is 90 degrees, which results in negative 60 degrees. Since the hour angle coordinate is measured using positive numbers only, we need to add 360 degrees in order to arrive at a positive result of 300 degrees or 20 hours. As the Earth rotates, the star's RA coordinate will stay at a constant angular separation from the vernal equinox, since its frame of reference is also rotating, but its hour angle coordinate will change based on the difference in sidereal time from the origin point. So 1 sidereal hour later, the entire RA system will have rotated 1 hour or 15 degrees westwards. Therefore, the star with an RA of 6 hours will still be located at a 90-degree angle relative to the vernal equinox, but its hour angle will have changed to 21 hours or 315 degrees since its position relative to the meridian has changed. Local hour angle is related to RA based on the observer's local sidereal time. For a given location, the local sidereal time, also called LST, is given by the right ascension of an object that has an hour angle of 0, meaning that it is currently located on the meridian. The LST is also equal to the local hour angle of the vernal equinox. The LST is related to Greenwich sidereal time in the observer's local longitude. Greenwich sidereal time, which is abbreviated GST, is just like the LST. It is the current right ascension of an object on the meridian as it would appear to an observer in Greenwich, England, which is located on the prime meridian, the 0 point for terrestrial longitude. The LST can be calculated by subtracting the observer's longitude, which is designated as lambda, measured positive eastward from 0, from the current GST. Make sure you convert your longitude into decimal hours by dividing by 15. Also, make sure you note the sign convention of your local longitude. Longitudes in the Western Hemisphere, west of the prime meridian, are designated as negative, meaning that they are the complementary angles of the positive eastern longitude. If you're located at a western longitude, in the United States for example, subtract your longitude from 360 in order to derive a positive eastern longitude. Once two of these variables are known, be it LST, RA, or local hour angle, the remaining variable can be solved. An object's right ascension can be converted to local hour angle by subtracting the object's right ascension from the LST. Likewise, an object's RA can be solved by subtracting the local hour angle from the LST. And lastly, the LST can be solved by adding the object's local hour angle to its RA. Make sure that the same units are being used for all variables, either degrees or decimal hours. If you're using degrees and you get a result that is negative, add 360 to the result, and if you get a result that is greater than 360, subtract 360. The same concept applies if you are using decimal hours. If negative, add 24, and if greater than 24, subtract 24. For a demonstration of the angular relationships between all these variables, let's take a look at an example. Here we can see the location of the Royal Observatory in Greenwich, England, which is located on the prime meridian with a latitude of 51.48 degrees north and 0.002 degrees east. To simplify things, we will assume the longitude of Greenwich in this example is equal to 0 degrees. Next, let's suppose that there is an observer located in Sarasota, Florida, with a latitude of 27.32 degrees north and a longitude of 82 degrees west. Since the longitude of this location is in the Western Hemisphere, it is designated as negative. In order to render a positive longitudinal offset in relation to Greenwich, we need to subtract our complementary western longitude from 360, which results in an eastern longitude of 360 minus 82 equals 278 degrees east. We can convert this into hours by dividing it by 15, which results in a positive eastward time offset of 18.533 hours, or a negative westward time offset of 5.466 hours. Next, let's suppose that the Greenwich sidereal time is 3 hours, which means that the vernal equinox will have a Greenwich hour angle of 3 hours or 45 degrees. We can represent the current position of the vernal equinox in relation to the two locations by overlaying the celestial sphere onto the globe. Now we can see that the longitudinal separation between the vernal equinox and Greenwich is equal to 45 degrees or 3 hours west of Greenwich, since the sidereal time of a location is measured from the vernal equinox in an eastward direction like longitude is. Since we know the time offset between Greenwich and Sarasota based on the longitude, we can add the Greenwich sidereal time to the longitudinal separation in hours in order to calculate the local sidereal time in Sarasota, which is equal to 3 plus 18.533 equals 21.533 hours, or 21 hours and 32 minutes. Another way to calculate the LST using a negative western longitude is to subtract the absolute value of the negative longitude from the GST. Just like before, if the answer is negative, add 24, and if the answer is greater than 24, then subtract 24. If we take a look at the sky in Sarasota, we can confirm that this result is accurate. Next, let's take a look at an example star. Capella is a system of 4 stars and 2 binary pairs, although it appears to be 1 star to observers on Earth. It is the third brightest star in the northern celestial hemisphere and has a declination of approximately 46 degrees and a right ascension coordinate of about 5.3 hours, or 79.5 degrees. Since we know the current location of the vernal equinox is 45 degrees west of Greenwich, we can conclude that Capella will be located 79.5 degrees east of the vernal equinox based on its RA coordinate, which results in a representative longitude of 79.5 minus 45 equals 34.5 degrees, or 2.3 hours east. Using the same method, we can calculate Capella's Greenwich hour angle, which is equal to the longitudinal separation between Capella and Greenwich, by subtracting Capella's RA coordinate of 5.3 hours from the current Greenwich sidereal time of 3 hours, which results in negative 2.3 hours. This result is negative since it was measured from Capella's representative longitude westwards to Greenwich. In order to render a positive result, we need to measure eastwards from Capella, which is analogous to adding 24 to our negative westward angle. This results in a positive Greenwich hour angle of 21.7 hours, which is equal to 21 hours and 42 minutes, or 325.5 degrees east. We can confirm this result by locating Capella in the sky of Greenwich and noting its apparent angular separation from the meridian. We can calculate the local hour angle of Capella as it appears to observers in Sarasota in a similar fashion. Since we know Sarasota's current sidereal time is 21.533 hours based on its longitudinal separation from Greenwich in the GST, we can calculate the local hour angle of Capella as it appears in Sarasota by subtracting Capella's RA coordinate from Sarasota's LST, which results in 21.533 minus 5.3 equals 16.233 hours, or 243.5 degrees. This result can be confirmed by noting the apparent angular offset of Capella from the meridian in the sky viewed from Sarasota. 3 sidereal hours later, the Earth will have rotated 45 degrees, which means that the vernal equinox will be located at a representative longitude of 45 plus 45 equals 90 degrees west of Greenwich, which indicates that the GST at this time will be 6 hours. And the Sarasota LST will be equal to 0.533 hours or 8 degrees. This angular offset applies to the entire RA system. Since Capella has an RA of 5.3 hours and the GST is currently 6 hours, we can calculate Capella's Greenwich hour angle by subtracting its RA from the GST, resulting in 0.7 hours or 10.5 degrees. The same method can be used to calculate Capella's local hour angle as it appears in Sarasota, resulting in 0.533 minus 5.3 plus 24 equals 19.233 hours, or 288.5 degrees. There are 2 differing forms of sidereal time. The form we have been focusing on is referred to as mean sidereal time, which is usually easier to calculate as it does not factor in the equation of the equinoxes, which accounts for the angular shift of the vernal equinox due to nutation of the Earth's axis, which is a wobbling motion or oscillation caused by the gravitational effects of the Sun, Moon, and other bodies in the solar system. We will talk more about nutation and precession in just a little bit. The apparent sidereal time is the version of sidereal time which does factor in the equation of the equinoxes. However, the difference between the 2 forms of sidereal time is rarely greater than 1 second. Calculation of the equation of the equinoxes will be covered in just a few moments. You can use this website in order to calculate the GMST or LST using a specific date and time, as well as your latitude and longitude. If you wish to calculate the GMST, use a longitude of 0. Instead of having to look up the current Greenwich mean sidereal time, it can be calculated using the GMST of a specific epoch. An epoch, pronounced either as epoch or epoch, is an indefinite unit of time. In astronomy, it is used as a reference or an origin point to determine parameters at a specific point in time, which is usually specified by a given date or year. For instance, the most commonly used epoch is called J2000, which refers to January 1st, 2000 at about 11 hours, 58 minutes, and 55.816 seconds, UTC, which is Coordinated Universal Time, which is basically the time zone that Greenwich is in. For our purposes, we will be using the epoch of 2018, the year in which this video was made, which refers to January 1st, 2018 at exactly midnight UTC, when the GST was approximately 6 hours, 42 minutes, and 22.6135 seconds. Our example epoch uses a time of midnight UTC instead of noon, as it simplifies calculations, since we are accustomed to calendar days beginning at midnight instead of noon. Once the GMST of a specific epoch is known, the GST of a given date can be calculated by multiplying the number of calendar days which have passed since the given epoch minus 1 by the difference between a solar and sidereal day, which is about 0.065709824 hours per day, and adding the result to the GST of the given epoch. It's important to note that for epochs beginning on January 1st, such as our example epoch, that the 1st of January counts as day 0 since it's the origin point, meaning that one calendar day must be subtracted from the total days from the epoch. This chart detailing the number of days in a given calendar year can be used to find the summation of days since the epoch date. Just remember to subtract 1 if you are using the example epoch. Also, be cautious to check if the current year or the year between the desired date and the epoch date are leap years, as this will affect the days attributed to each month. Leap years happen every 4 years, starting from 2000, so 2016 was the most recent leap year, 2020 will be the next, then 2024, etc. Basically, a leap year occurs on a year which is equal to any multiple of 4 plus 2000. After the sidereal correction for the number of days, the next step is to multiply the desired time of day, in UTC time, by the quotient of a solar and sidereal day, which is about 1.00273791, and then add the result to the total. If you are using your local time zone, make sure to convert it to UTC first. Remember that epochs, such as J2000, are usually based on an origin time of noon, since they use Julian days as a reference point. More on this in a minute. So you will need to subtract 12 from the desired UTC time if you are using an epoch like J2000. However, our example epoch of 2018 is based on a time of midnight, so no adjustment is required. As was the case previously, if the result is greater than 24, then subtract 24 hours. If the date used in the calculations is many decades ahead of the epoch, you may need to subtract multiples of 24 to arrive at a suitable answer. This will give you an accurate GMST of the date and time used in the calculation. For example, to calculate the GMST on April 10, 2018 at 10 hours, 30 minutes, and 24 seconds Eastern Standard Time using the GMST of the 2018 epoch, the calendar days elapsed since the epoch would be equal to 89 days from January 1st to April 1st. Since 2018 is a standard calendar year, plus 10 days for the date, which equals 99 days in total. Remember to subtract 1 from the summation of days, since the January 1st calendar day counts as day 0. After multiplying this by the constant 0.0657098,244, the result will give the compensation between solar and sidereal days for the days which have passed since the epoch date. Next, we need to convert the Eastern Standard Time to UTC time. Since Eastern Standard Time is 5 hours behind UTC, we need to add 5 hours to our desired EST, which results in 15 hours, 30 minutes, and 24 seconds UTC. Next, we need to convert this time to a decimal, then multiply it by 1.00273791 in order to account for the discrepancy between solar and sidereal time, which results in a value of 15.549122252 hours. Next, we total the GMST from the 2018 epoch date, the sidereal time passage due to sidereal versus solar days result, and the compensated time result, which results in 28.7606 sidereal hours. After subtracting 24 from the result, we arrive at a GMST for the specified date and time of 4.7606766678 hours, which is equal to about 4 hours, 45 minutes, and 38.436 seconds, or about 71.41 degrees. The result of our example is off by approximately 0.002798 seconds, or 0.042 degrees. After the GMST of the desired date is known, the LMST can be calculated using the methods mentioned earlier, using the observer's longitude. The reason that the GMST must be calculated prior to the calculation of the LMST, as opposed to using the local time zone to calculate the LMST in a single step, is due to the fact that time zones such as Eastern Standard Time are used for a broad span of longitudes, which may cause inaccuracies. For example, the Eastern Standard Time zone corresponds to -5 hours from UTC, which is equal to a longitude of 75 west. This means that if an observer at a longitude of 82 west, or -5.4666 hours, used the Eastern Standard Time to calculate their LMST, their calculation would be off by 0.468 hours, or about 28 minutes and 4.6 seconds. There is another method of calculating the GMST which involves another commonly used temporal system in astronomical calculations, which is referred to as either the Julian Day Number or Julian Date, abbreviated JDN or JD, which has an epoch corresponding to the start of the Julian period on January 1st 4713 BC, at exactly noon UTC based on the Julian calendar. This date was chosen as it coincides with the start of 3 differing cycles: the lunar cycle, the solar cycle, and the induction cycle used in medieval time. So the time passed since this specific epoch could easily be used to calculate the progression of each cycle. The Julian Day Number is a count of solar days since that epoch based on a time of noon, with the passage of 1 solar day representing an integer of 1 Julian day. This indicates that 1 solar hour equals 1/24th of a Julian day, 1 solar minute equals 1/1440th of a Julian day, and 1 solar second equals 1/86,400th of a Julian day. A Julian date commonly used in calculations is that of J2000, corresponding to a JD of 2,451,545. The reason that the Julian date is useful is that it is not affected by time modifiers, such as leap days, leap seconds, etc. It is just the count of solar days since the epoch date, so it is an accurate and universal way to calculate a specific date in time without having to deal with other calculations which may be required using other calendars. An alternate version of the Julian date is the modified Julian day, MJD, which is equal to the current Julian date minus 2,400,000.5. Unlike the Julian date, the modified Julian date corresponds to a time of midnight UTC, as indicated by the 0.5 used in the calculation. The following equation can be used to calculate the Julian day number using the month, day, and year from the standard Gregorian calendar in conjunction with the desired UTC time. The upper terms within the parentheses are used to calculate the Julian day number, while the terms below involving hours, minutes, and seconds are used to calculate the fractional Julian day. The bars with the feet represent the floor function, which is used to round down to the nearest integer. There is an important caveat for using this formula for the months of January and February. For non-leap years, if you are calculating a date in January, add 2 to the result, and if you are calculating a date during February, add 3 to the result. For leap years, add 1 to the result for dates in January, and add 2 for dates in February. For our example of Julian date calculation, we will use the previously used date of April 10th, 2018 at 15 hours, 30 minutes, and 24 seconds UTC. Using this date and time, we will define the variables to be used. D is equal to 10, M equals 4, Y equals 2018, H equals 15, M equals 30, and S equals 24. The first term in the equation concerning the month variable equals 153. The next term containing the year equals 2,459,593, and the following term also containing the year is equal to negative 15. Next, we sum the results of the individual terms with the day variable of 10, and subsequently subtract 1,522 from the summation, which results in a Julian day number of 2,458,219. Next, we need to calculate the fractional day using the time variables, which gives a result of 0.146111. The final step is to add the day number and the fractional day together, rendering a final answer of 2,458,219.146111. Other notable Julian dates include the epoch we used earlier of January 1st, 2018 at midnight UTC, which has a corresponding Julian date of 2,458,119.5, and the J2000 epoch based on UTC noon has a Julian date of 2,451,545. The Julian date is used in an alternate calculation of the GMST, as it is easier to calculate the number of days which have passed since an epoch date using the JD number as opposed to summing the number of calendar days since an epoch and subtracting 1. This is especially true for dates which are far ahead of the epoch used in the calculations. The calculation of the GMST using the Julian date is similar to the equation used earlier, except that the days variable used previously is replaced with the term in floor brackets, which subtracts the Julian date of interest, represented by the variable j, from the Julian date of the given epoch, which is represented by the variable j sub e. This determines the day since epoch as an integer. The time component of this equation is exactly the same as before. It's important to note that the Julian date of the given epoch must correspond to the GMST of epoch used in the equation. This means that if you wish to use the epoch of J2000 for the GMST of epoch, then J2000 must be used for the Julian date of epoch as well. For an example of the Julian form of the GMST calculation, we will use the Julian date we calculated earlier, which is 2 2,458,219.14611, corresponding to April 10, 2018 at 15:30:24 UTC. This will be used as the Julian date variable j. As was the case previously, we will use the 2018 epoch, which corresponds to the GMST of 2018 being equal to 6.70628158, and the Julian date of 2018 being equal to 2,458,119.5. The time variable t is equal to 15.5066, just like the previous GMST calculation. The first step is to solve for the term in floor brackets, which equals 99 days after rounding down. After multiplying this by the constant 0.065709824, we arrive at a result of 6.50522726. Next, we need to solve for the time compensation just like we did in the previous GMST equation, resulting in 15.54912252. Next, we sum these two results with the GMST of 2018, which renders a result of 28.76067668. After subtracting 24 from this result, we arrive at a final answer of 4.76067668 hours, or 4 hours, 45 minutes, and 38.436041 seconds, which is exactly the same as the answer from the original GMST calculation. If you are interested in obtaining the GMST or Julian date and are not inclined to the fairly lengthy calculations involved, you can use the link shown earlier to obtain the GMST, LMST, or Julian date. Just remember to include your latitude and longitude if you are calculating the LMST. As noted earlier, the projection of the equatorial system is completely dependent upon the orientation of the celestial poles, which also serve as the Earth's axis of rotation. The angular position of the poles in relation to the ecliptic changes over a period of about 25,600 years due to a cycle referred to as either axial precession or precession of the equinoxes. This causes the apparent position of the celestial poles to move relative to the fixed background stars in the direction opposite of the Sun's apparent motion at a rate of about 50.67 arcseconds per year. This apparent angular offset applies to the entire equatorial system, causing the coordinates for a given object as well as the equinoxes to shift at the same rate. As the axis of the Earth precesses, the poles appear to trace a circular path in the sky, called precession circles, which have an apparent angular radius based on the current obliquity or tilt of the axis. As the poles precess, they point to differing stars, which are called pole stars. The current North Pole star is Polaris, aptly named after the pole, which has a declination of about 89.34 degrees. But in the year 13,650 AD, the pole star will be the much brighter Vega, although it will be farther from the pole compared to Polaris with a declination of 84.53 degrees. Because of the effect of precession, there are multiple versions of the equatorial system based on the projection of the system at differing epochs, with the J2000 epoch serving as the astronomical standard. The version of the equatorial system based on the present time is called the of-date version. So when using equatorial coordinates, make sure you clarify which epoch is being used for the system. Basically, axial precession is caused by the application of torque to the Earth's axis, which is provided via non-uniform forces called tidal forces. These tidal forces are the net result of a gravitational gradient from a body, primarily the Moon and Sun, which acts upon the Earth's equatorial bulge, where the moment of inertia is weaker compared to the axis of rotation due to the centripetal forces of Earth's rotation. The components of this differential force parallel with the axis are responsible for precession, as they apply a torque vector to the axis directed towards the ecliptic plane. The Moon accounts for 68.52% of forces involved in precession, while the Sun accounts for about 31.47%, with all other bodies accounting for 0.004%. The forces responsible for precession also affect the tilt of the axis. The tilt of the Earth is referred to as obliquity. Earth's axis is currently tilted about 23.44 degrees relative to the ecliptic plane, and fluctuates between 22.1 to 24.5 degrees, based on a 41,000-year cycle. This indicates that our current era corresponds to the average obliquity in this cycle. As time goes on, the obliquity will begin to change, corresponding to more extreme climates during the winter and summer. In addition to the precession of the poles, which follows a circular path, the Earth's axis undergoes a cycle called nutation, which is derived from the Latin word for nod, which are other small oscillations or wobbling motions which resemble ellipses if isolated from the path of precession. The cycle has many components, but the dominant lunar nutation cycle has a frequency of about 18.6 years, indicating that about 1,376.34 nutation cycles happen for each precession cycle. There are two different components of the nutation waveform. The first is the nutation of longitude, which affects the movement of the equinoxes like precession. Longitudinal nutation can be thought of as the frequency of the wave, with half of a cycle being equal to about 6.86 arcseconds over 9.3 years. The second component is nutation in obliquity, which affects the axial tilt of the Earth. Nutation in obliquity is synonymous with the amplitude of the wave, and results in the deviation of the path of the axis from that of a circle with a maximum angular amplitude of about 9.22 arcseconds. Nutation is similar to precession in that it is caused by the perturbing gravitational forces of other bodies in the solar system. However, nutation is different in that it is created specifically by the precession of the orbital planes, eccentricity of the orbits, and the position of these bodies in relation to Earth over time. As was the case with precession, the Moon is the dominant player in the nutation of the axis, with the frequency of the primary nutation term, 18.6 years, being equal to the period of precession of the lunar ascending node. The precession of the lunar ascending node has a large influence over nutation. Due to the Earth's obliquity, the Earth's equator is currently inclined by about 23.44 degrees relative to the ecliptic. However, the lunar orbit is inclined to the ecliptic by about 5.15 degrees, meaning that the inclination of the lunar orbit in relation to the equator fluctuates from about 18.29 degrees to 28.59 degrees during the 18-year cycle of the precession of the lunar ascending node. This change in inclination changes the orientation of the gravitational force from the Moon, which subsequently results in the nutation of the Earth's axis. The equation of the equinoxes, used to calculate the apparent version of sidereal time, is based upon a simplified version of the components of the nutation equations, using the Julian Day Number to calculate the change in variables over time. Once the equation of the equinoxes is calculated, the result is added to the corresponding mean sidereal time in order to arrive at the apparent sidereal time in units of hours. The variable j used in this equation is the number of Julian days which have passed since the 2018 epoch used in our earlier examples. To find the value of j, convert the desired date and time into the Julian Day Number via the equation used previously or via the calculator link, then subtract the Julian date of the 2018 epoch, which is equal to 2,458,119.5. This will give the time offset relative to the epoch in units of Julian days. Plug this variable into the equation of the equinoxes shown here, and then add the result to either the LMST or the GMST to arrive at the LAST or GAST. It is important to note that the values used in the calculation of the trigonomic functions shown here are in units of degrees, not radians, and that the result of the equation of the equinoxes will be in units of hours, so ensure that the mean sidereal time you use is also in units of hours. For our example of the calculation of apparent sidereal time, we will use the date of April 10th, 2018 at 15:30:24 UTC, which has a Julian date corresponding to 2,458,219.14611. To find the value of j, we need to subtract the Julian date of the 2018 epoch from the JD of our example date, resulting in 99.64611. Next, we plug the value of j into the first term of the equation of the equinoxes, which results in a value of 2.3858 times 10 to the power of negative 4. Next, we do the same for the remaining two terms, resulting in values of 1.4687 times 10 to the power of negative 5 and 0.9175 respectively. Now that we have all the values we need, we can calculate the equation of the equinoxes by subtracting the second term from the first term, then multiply the result by the third term in order to arrive at a value of negative 2.3228 times 10 to the power of negative 4 hours, which is equal to negative 0.8362 seconds. The final step is to sum the GMST of the example date with the equation of the equinoxes, resulting in a Greenwich apparent sidereal time of 4.760444 hours, or 4 hours, 45 minutes, and 37.5998 seconds. Hopefully this video has been useful for those interested in learning about celestial coordinate systems. In the next video we will delve into some astrophotography calculations, starting with static exposure equations which are used for wide field tripod exposures, as well as field of view calculations, which are useful for determining the sky coverage of a specific lens and sensor combination. We will also be covering pixel field of view equations, which help gauge the angular coverage of objects and are especially useful in planetary imaging and guiding. Here's a list of programs used to create graphics and images throughout the video. If you have any questions, I would be happy to assist you. Thanks for watching.